Hello everyone, my name is Aditraj and in this video I'm gonna talk about how to implement a 4:1 multiplexer using decoder and tri-state buffer. Later on we will also discuss about the Verilog code for the implementation of 4:1 MUX using decoder and tri-state buffers. So this is our course agenda. First we will talk about the decoder circuit, what will be the decoder do and different types of decoders. Then we will go through multiplexers and also we will go through the 4:1 multiplexers. Then we will talk about buffers, different types of buffers like trusted buffers, and after that we will implement a 4:1 multiplexer using these decoders and also tri-state buffers. Then we will go with the Verilog code for it. So let's start with decoder. So a decoder circuit is nothing but we can say like it can convert a machine understandable language to a human understandable language. And decoder can also be defined like it can convert n input signals into 2 to the power n unique output signals. So as we all know, like with the help of n is to 2 to the power n decoder, we can generate like all the min terms or the max terms of n input variables depending upon how we take the outputs. When we take active high outputs, then the decoder circuit will generate all the possible minterms, and when we take active low output, then the decoder circuit will generate all possible max terms. So here it here I have shown a example of 2 is to 4 decoder circuits. In this decoder circuit, as I have taken active high output, so this decoder circuit will produce all the possible min terms regarding the input variables d naught and d1. So here we have seen like y naught is equal to d1 bars and d naught bars, y1 equal to d1 bars d naught, y2 equal to d1 and d naught bar, and y3 equal to d1 d naught. So these all are minterms for d1 and d naught. So with the help of n to 2 to the power n decoders, for n variable we can implement and we can generate all possible minterms for n number of variables. So now we will talk about the multiplexer circuits. So what is multiplexers? So multiplexer is nothing but it is a device which can take 2 to the power n number of inputs along with n number of select inputs and produce a single output. So how it can produce a single output? So it will depends on the selection combination of selection line. So depending upon the combination of selection line, one of the input will be routed to the output. So with that we can implement a multiplexer circuit. So here I have shown an example of 4:1 multiplexer circuit. In this the number of inputs will be 4, and the relation between number of inputs and selection line are like inputs is like if we take n is a number of input, n is a number of selection line, and then the number of inputs will be get equal to 2 to the power n. So for 4:1 multiplexer, there is a 4 input lines and 2 select lines, and depending upon these 2 select lines, one of the input will be routed to the outputs. And here for also we have written this is called Shannon's expression for 4:1 multiplexers. So here we have seen like if we take like if we suppose if we have two variables s1 and s0. Okay, suppose we have two variables like s1 and s0. Then for s1 and s0, we like in this expression we have seen like these s1 and s0 will generate four minterms like this: s1 bar, s0 bar, s1 bar, s0, s1 bar, s0, s1 s0 bar, and s1 s0. Okay, so if we like from that idea we can thought of like we can also implement 4:1 multiplexer with the help of decoder, as a decoder will produce all the possible midterms for its input variable. So if apply input to a 2:4 decoder, then we get outputs like s1 bar and s0 and s1 bar s0 like that. Okay, So with the help of decoders, we can generate the minterms. And let so first we will talk about the tri-state buffers. Let's first we talk about the tri-state buffers. So what the tri-state buffer does, like tri-state buffer is nothing but like buffer is a circuit which can just take the input and produce at the output. So but in tri-state buffer there will be a controlling inputs, like we can control when the input goes to the output. Like if we apply the control input as active high, then the input will be connected to the output. Otherwise, if if input will be low, then the output will be in high impedance state. So this is called active high control input tri-state buffers. And we can also implement a active low control tri-state buffers. In this, if the control input is 0, then this will be act like buffers. And if the control input is 1, then it will act like a high impedance state, like open circuits. So with that, we can implement, and with the help of decoders and tri-state buffers, we can implement a 4:1 multiplexer. Let's check the functionality of the 4:1 multiplexer using these decoders and tri-state buffer circuit. So suppose I have I have I have taken I have supplied the input to selection line of the multiplexer as a input to the 2:4 decoders. Then from here we can generate all possible minterms corresponding to the selection line. So here we like w of 0 will be correspond to s selection line, like s0 bar and s1 bars. W1 will be S1 bar and S0, and W2 will be S1 S0 bar, and W3 will be S1 S0. So depending upon these, we can generate all the possible combination of selection line. And with if we apply the if we apply the these combination of selection line to the input, to the control input of the buffer, so whenever the one of the input will be high, then only the then only the input will be routed to the outputs. And at a time, as we know, at a time only one input combination will be one input combination of the selection element will be high. So at a time only one of the input will be routed to the output. This is that the multiplexer have does. So with that, we can also implement a 4:1 multiplexer using a 2:4 decoder and a tri-state buffers. So let's go with the go with Verilog code. Now let's go with Verilog code for 2:4 decoders and tri-state buffers. And later on, we will instantiate these modules in a 4:1 multiplexers, Verilog code. So first we will go through with the Verilog code for 2:4 decoders. So as we can write, these are the input combination of D1 and D0. Like here is two input variables D1 and D0, and the output number of output variables will be 4. So we have to instantiate these two inputs and output in a decoder module. So I have first written the module name, like my module name, and ports number and different ports, like what are the ports available into the these modules. So I have written like module sorry I have written like module decoder 2:4 in and output, because it's here only input and output will be present. So I have specified the direction of these variables, like in act as a two input variable. So I have written a vector in a vector form, like one down to 0. Here one will be the MSB and 0 will be the LSB. So as I have written input as a two-bit variables and output as a 4-bit variables. So for every output we have to assign a boolean expression. So here we follow the behavioral modeling. So I have assigned output for every single output. I have assigned some input combination, like assign output out 0 for LSB. Like here you can compare like y from out 0 with y naught. So here out 0 can be written as a bar d1 bar, say here y naught will be written as d1 bar and d naught bar. So similarly we can write here out 0 is equal to nothing but input 0 bar and input 1 bar, because here two different input will be input 0 and input 1. Similarly we can write for 1, 2 and 3 also. So with this we can write the code for 2:4 decoders. Now Now we can write the code. We can also write the code for the buffer circuit. So for buffer circuit, as we have know, like whenever the control input signal goes high, then only the input will be equal to output. Same thing we can write in behavioral fashion in Verilog code also. Like first we have to retain the all ports in the modules in our modules. So I have written like module buffers, module, and module name is buffer, and ports are in enable and outputs. So I have also give their direction, like input will be our in and enable signals, and output will be our output signals. Here we can specify the type of the variables, like which type of the variables we can write. So here the output our output variable out is a res type variables, whereas by default in Verilog, by default the variable will be in wire type. So our input variable is in wire type, but our output variable is res type. Why we write for output variable as a res type? Because we have used the output variable as a left hand side of the blocking statement, which are we are gonna learn in Verilog modules. But here you can just written like output res output read out. So because in procedural assignment, whichever will be present in left side, we have to specify a res type variable. Okay, so with this we can write output res out. Now ignore for for will time mean will time, because we have learned about this also in Verilog code. So first, so how we can write the code for it? So always at the rate stars means whenever the any one of the variable will be changes, like always any one of the variable will be changes, you have to execute this code. What code? This begin in between begin and end. What is the in between begin and end? If enable is high, if enable is high, then output equal to input. If enable is high, then output equal to input, else output is equal to high impedance state. Same thing, we are going to talk about the definition of tri-state buffers. Like whenever the control input is high, then output will be equal to input. But whenever the control input is low or zero, we can say the output will be in high impedance state. Same thing I have written in Verilog. So now we are we are we can implement a 4:1 multiplexer using decoders and buffers. For implementation of these 4:1 this 4:1 multiplexer, we have to just instantiate these modules in 4:1 multiplexer modules. So how we can instantiate these modules? So for instantiation, first we will see how the 4:1 multiplexer have written module have written. So I have written like module and module name. My module name here, my module name is 4:1 multiplexer. Like we have to implement using decoders and buffers, so I have just write decoders and buffers. And here the ports are present. These are the ports present in the multiplexer, 4:1 multiplexer. What are the ports? Like in, select line, and outputs. So I have defined input as a 4-bit variable because I have to implement 4. Number of inputs will be 4. So I have defined input as a 4-bit variable in, and also in, and also I have an input of selection line which is a 2-bit variable. So I have write input 1 down to 0. Here 1 is the MSB, here 3 is the MSB, and output is a single bit variable. So I have written as output equal to out. And what is the means of wires? Wire is nothing but the in between present for the connection in between the modules. Like for the connection of in between the modules, we have just we have just written a wire 4 bit down 3 down to 0, that is W of 4-bit variables. So I've just written a wire type variable W, which is used in connecting between the different modules. So first I have instantiated this decoder circuit. This so first I have instantiated decoder 2:4. Because why I write a decoder 2:4? Because in decoder circuit, if you see, my module name is decoder 2:4. So same module name we have to instantiate here, decoder 2:4. And this is the number of we can assign anything like a D1, D2, D0, or anything which you want. So here we can write D1, and then select line as a act as a input to the decoder. So same way, like we have instantiate the ports here, in same way we have to instantiate the ports here also. and in same order, but same order, we can say in same order, but we can assign instantiate in different order also. But for that different modeling style will be used, different different instantiation style will be used. But here just using same order, so I have written like input as a cell selection line and output as a w wires. So this is the instantiation of the modules of buffer. This is the instantiation of module decoder. And now we have to instantiate the four modules for the buffer circuit, because we have used four buffer circuit. So I have instantiated four times the buffers. So I have written like as I have written the module name of buffer is itself buffer. So here also I have written buffer, and this is b1. So it act like b1 buffer. And in same order like in buffer, how we written the different ports, in same order we have to write here also like enable input here, input act as a in0 and in 0, and enable circuit enable input will be act as like w0, and output will be act as t0. In same order we have to write. So similarly we can write buffer 1, buffer 2, buffer 3, and buffer 4. And after that, because at a time only one of the output, one of the t1, t0, and t2, t3 will be assigned to the output. So we have to retain also what to, among these four, which one will be goes to the output. So for this we have to write assign out equal to t select. Why we like t select? Because t select will be combination of two bits, and with the help of two numbers, two bits, we can generate four combination. And here the t will be here the t will be also in mm, mm, t will be also a 4-bit variable. So with the help of selection line we can generate the all combination of t. And whenever the this selection, which selection line will be present, like when like suppose we have applied the selection line at 0 1, that is 1 1, then among this, so 0 1 will be high, 0 1, so the w1 will be high, and upward w1 will be high. So this only t1 will produce the input to the output, but all the other will be at high impedance. So if we connect all with the output, so the output will be shown like x undeterminate. What should be the output? Like this is high impedance, this is 1, this is high impedance, this is high impedance. So output got confused, and this will produce a undefined state x, or don't care x. So for this, for this we have to assign like output equal to t select. So whichever the selection combination of selection line, that is 0 1, 0 1 will be corresponding to 1. So the 1 will be routed, so input 1 will be routed to the output. So similarly we can if specify 1 1, so corresponding to 1 1, w3 will be high and w3 will be high, so in 3 will goes to the output. And similarly we can, as we have assigned output at t of selection line. So as selection line combination will be 1 1, so t3 will be selected, so t3 will be selected as output. So with this we can implement the Verilog code for the 4:1 multiplexer. Okay, so now we have to write also a test bench. So for test bench we can write module name. We can specify module name as MUX 4:1 tb. And for for a test bench written, we have to specify input as a range variable and output as a wire. So in 4:1 multiplexer in stimuli, so input act as a like 4-bit variable. So we have a specify, right? Suppose we have write a as a input to the stimulus of 4:1 UUT or 4:1 multi modules. So I have a specified range 3 down to 0 A, and also 2-bit selection line. So I have a specified range 1 down to 0 and a wire outputs. Here we have a specify a integer type variables I for generating a combination of for the selection line inputs. So I have instantiated the modules 4:1 here, 4:1 here. Sorry for this is wrong. I have written 4:1 mux decoders and buffers. So in code you have to write 4 is mux 4:1 4:1 underscore decoder underscore buffer uut as out. And with and after that we can initially suppose we can write initials begin and with the help of, suppose we have initially assigned input as a equal to 4 bit hexadecimal b equal to, what is b equal to 11, 11 means 1011. And for the selection line input, we can generate with the help of a loop, like for I equal to 0 and I less than 4, I plus plus, we can generate s equal to I, like s will be first be s will be 0 0, and after 10 unit time again for loop will be begins, then again the s equal to 0 1, and again after 10 unit of time. Similarly this will be happen and completed for I less than 4. And this how we can generate all the possible combination of I here. So with this we can write the test bench. Okay, so now let's verify it, how it can work and how we implement on it on different like how we can simulate or how we can synthesize these circuits. Okay, so for this you can create a Verilog folder in on desktop, or you have to create 4 folders like RTL, simulation, synthesis, and TV. Okay, so after that, you in RTL you have to write code. So for writing a code, you can use Notepad plus plus, Notepad plus plus. Okay, so here I have written the code. First, we have instantiated the modules: 4:1 multiplexer, decoder, buffer, input, and select, as I have explained in the PPT. So with, this is how we can write the code for multiplexers, and and for different modules I have written like decoders 2:4 and also buffers. And you have to save all these files to this RTL folder, this PC, desktop, Verilog, and RTL. Okay, so here RTL I have saved buffer, decoder, multiplexer, 4:1 decoder, buffers. I have saved all these 3 files here. Okay, so after saving these files, and you have to also write the test bench for it. So you have also saved from the Notepad plus plus, you have saved test bench files also. Okay, so after saving these 2 files, and you have also create two folders separately, for one for the simulation purpose, here. Suppose I have deleted this folder. Okay, so one for the simulation purpose, and one for the synthesis purpose. Okay, so now first we are gonna simulate this file. So let's use, for simulation we have to use model sim. Okay, so we gonna open to the model sim. So in model sim we have to go to the jump start, then we have to create a project. So for this we have to create a project. Now here we have to specify project name and project location. So as I have told you, we have to create a folder for simulation purpose, so which is written as sim name. The folder name is sim, so we have to browse to it. So I am in my desktop, I have placed a Verilog folders, and in Verilog I have a folder sim, so we have to select this folder sim. Okay, so after selecting this we have to specify name. Suppose I have specified MUX 4:1. Okay, so then you have to click at OK. Now as I have written already the Verilog code files, so you have to go to the add existing files. Okay, so after add existing files you have to browse, and you have to go into the RTL folders, and from RTL folders you have you have you have take all these 3 codes, like you have select all these 3, and you have to click open. And after this you have shown all these 3 files will be present here. Okay, so after this we have to also add the test bench files. So again for the adding of test bench files you have to go with the add existing files, then you have to browse to the folder tb and add to these files. Okay, now I have added 4 files. One is for TV. The second is the main module, which is we have to go, which we are gonna to be implemented, and then the instantiation modules. Okay, then you can close it. And now we have to come, as the status will be unknown. Like the compile here, the compilation is not done. So first we have to compile all these 3. So for that you have to select all these files and go and and you have to click right click, and then you go to the compile and select compile selected. after that, after the completion, you got here, you can see the result for your compilation, like our compilation is done successfully or not. So if any error will be present, then then here the error will be, then those error will be here, shown here. Okay, so here this is showing 4 compiles and 0 file with no errors. So the all the four files will be compiled successfully. Okay, so now we have to simulate it. So for that we have to go to the simulate, start simulation, go into the work, and for in work we have to select TV, like what we want to display in display, or what we want to check, like so for that we have to select TV. In TV we have written output and input, so we have to select TV. Okay, so after that click on OK. So the waveform window will be appear. So in that you have to select this and click on right, add to the waveform, and after adding to the waveform you can click on here, run all. Okay, so after that a pop-up window will be appear. Are you sure you want to finish? So you have to select no. Okay, so here you got the waveforms, and also here you can also check display your output, that our output is correct or not. From waveform you can also check, and from here also you can check. Suppose our input is for in zero time, our input is 1011, and our selection line input is 00. So depending upon 00 line, which of the input will be selected, this first LSB you have to select, so the output will be shown here is 1. Okay, so this is correct. So next 01, 01 when 1 will be 1 1, 10 10 will be 0 0. So 11 11 will be 1 1. Again we have to apply different inputs like 0011. So in 00 1 will be selected, 01 1 will be selected, 10 10 we have 0, so 0 will be selected, 11 we have 0 0 will be selected. So similarly we can verify all these three, and same thing you can verify from your waveform also, like this is our inputs, and this is our selection line inputs, and depending upon the selection line inputs, this is our the output signals. Okay, so 00 the output will be 1, 01 the output will be 1, 10 the output will be 0, 11 the output will be 1. Similarly here for this timing the simulator will be off, and for this again we have to apply again the different inputs 0 1 1. So 00 the output will be 1, 01 the output will be 1, and 10 the output will be 0, and 1 output will be 0. Okay, so in that way we can check our simulation result, and we can also show in that our before simulation our sim folder will be empty. So but after the simulation, here the whatever the whatever we have done, so here a work, so model sim a file will be generated. Okay, so now we have to synthesize our result. So for that synthesize we have to use the quartus prime. So now we have to open the quartus prime. Okay, so in quartus prime we have to go with new project, we have to click next. Same, we have to browse through the our folders. So our folder present on the desktop in Verilog, and we have to select now synthesis folder. So because we are going to synthesize our design, so we have to select synthesis folder, select folders. Then you can, in that you have to specify same name which are the your modules name. Okay, so I have written MUX 4:1 underscore decoder underscore buffer. Okay, so after that you have to select next, empty project, next. Now you have to add the files. So for that you have to go to the RTL of that folders. So I go to the RTLs, you have to select all these three files, click on open, click on next. Okay, so these are the something you can skip, next, next, and Now you can finish. Okay, so after the opening the project, here the project file will be shown. Our project file will be shown like mux full, yeah, this. So here the mux file will be shown, so you have to compile this. So click here, wait for some time to compile the our design. Here the compilation is going in progress, 1%. So after the completion of design we can see our result. Okay, so the message is showing like quarters prime full compilation was successful, 0 errors and 17 warnings. You can ignore these warnings for a meantime. So now you have to go to the analysis and synthesis. Scroll down, you have to go to the netlist viewers, and in this you have to double click on RTL viewers. So from that you can see your RTL schematic design. So here this is our the design of 4 is to 1 multiplexer using decoders and buffer circuits. This is our decoder circuit. This is our buffer circuit. Yeah. So this is our complete RTL schematic. Okay. With this, I have come to the end of this video. Thank you.